Hi, so in this video we're going to be looking at simple harmonic motion. This is going to be part 3 of the MCQ series. Okay, so this is question 15 or 16. I think it's question 16. So now in this case, a particle is performing simple harmonic motion. So what is the phase difference between the displacement and the acceleration of the particle? Okay, so the best way to sort of understand this would be to look at would be to just graph the functions of displacement and acceleration. So we are looking at the phase difference between displacement and acceleration. Okay, so in this case, let's say if I draw this following graph. So on my y-axis, let's say if I've got displacement, and then on the x-axis I've got time. Okay, now let's say that our displacement function x with time, let's say if this is of the form sine of t. Okay, so we know that in simple harmonic motion, the actual equation is x of t is x naught sine of omega naught t, right? You don't need to know this in SL, but the x of t, it can take the form of x naught sine of omega naught t or x naught cosine of omega naught t, right? And in this case, x naught is the amplitude. Okay, so in this case, when we have these functions, the reason why we get these sine and cosine functions deals with differential equations. Okay, so the basic idea for it is that we end up getting this equation that the acceleration is negative k by m multiplied by x, and you can actually say that mass times acceleration is negative kx. So this is just your Hooke's law. And essentially what you can say is that the acceleration is the double derivative of the displacement. So m times d squared x by dt squared plus kx is equal to 0. So the reason you get this double derivative is because if you take your displacement and divide it by time, you get the velocity. And then if you take the velocity and divide it by the time, you get acceleration. So acceleration is sort of related to the displacement, right? And so in this case, what's going to be happening is that if you take the gradient of a displacement time graph, so if you have a displacement time graph, and if you take the gradient of a point, then you get the instantaneous velocity. So the gradient of that graph gives you the instantaneous velocity. And I've explained this before, but when you take a velocity time graph, and let's say you take a gradient at a particular point, then the instantaneous gradient at that point gives you the acceleration at that point. So we use derivatives because we're trying to find gradients. So whenever you think of differentiation, you should relate it to the idea of gradients. Okay, so ultimately you get this differential equation where m times so in this case m times d squared x by dt squared plus kx is 0. So the mass is a constant and the spring constant is also a constant. So the only unknown variable over here you would have is x. So you're writing an equation where you have an unknown variable and you have the derivatives of that variable. So it's a differential equation. And when we solve these differential equations, we get the form that x of t is either x naught sine of omega naught t or x naught cosine of omega naught t. Okay, so the main thing is that when you go over the concept videos, you should realize that the displacement, velocity, and acceleration are sine and cosine functions of time. Okay, that's what you need to know for the SL. And then for HL, you would need to know the actual equations, right? Now, in this case, what's going to be happening is, let us say that our displacement x is of the form of sine of t. Okay, so therefore, we are going to graph this function of sine. So we know that the sine function fluctuates from positive 1 to negative 1. We know that the value of a sine function is going to be positive 1 at 90 degrees. It's 0 at 0 degrees, and then at 180 degrees it's 0. At 270 degrees it's negative 1, and then at 360 degrees it's 0. Okay, so that's your corresponding sine function that we have drawn. Okay, now we know that the d by dt of sine of t, so this is your displacement function. If you take the derivative of that, then you get cosine of t. So this is your velocity function. Okay, and then if you take d by dt of cosine of t, then you get negative sine of t, which is your acceleration function. Okay, so if you take the derivative of your displacement, you get the velocity. So think of it, if you take the instantaneous gradient of the displacement time graph, you get velocity, right? And then if you take the instantaneous gradient dv by dt of a velocity time graph, you get acceleration. So we just did dx by dt for sine of t, so we got the velocity as cosine of t. And then we did dv by dt for cosine of t, and then we got the acceleration as negative sine of t. Okay, so we have determined that in this case our acceleration function is going to be negative. The acceleration function is going to be negative sine of t. So we can graph negative sine of t over here. So what you can see is that if you have a function y is equal to f of x, then if you want to graph a function negative f of x, all you do is that you reflect it on the x-axis. So think of the x-axis as a mirror, and you can make a reflection on that x-axis. Okay, so we're going to reflect our displacement function, which is sine of t, on the x-axis. And so if you make the displacement, we get this function over here. Okay, now once again we'll draw all the angles. So we know that this is 180 degrees, this dot. We know this is 0 degrees, and we know that this is 360 degrees. Okay, so the black function becomes the acceleration function. The black function is the displacement function, x of t, and the red function becomes the acceleration function. Okay, now in this case, if you look at the phase difference, so phase difference is sort of like the difference in the angles, right? If you look at the phase difference over here, just one second. So let's make this continuous. Okay, so in this case, let's say if I take this graph of acceleration, right, and if I just move it a little bit to the left, I'm going to get the sine function. So what you'll see over here is that this black sine function is going to be going back. So this oscillation for the sine function will keep happening. Okay, so you'll get this sort of movement for the sine function as it keeps going. So what this means is this angle over here is negative 180 degrees, and this angle over here is negative 360 degrees, right? Now if I take this acceleration function, okay, so this is the acceleration function. If I take it and I move it to the left by 180 degrees, so as you can see, I'm going from, as you can see over here, just watch these 2 points. Okay, so in this case, as you can see, in this blue point, I'm moving it to the left by 180 degrees, right? So I'm taking this acceleration function and I'm moving it to the left by 180 degrees. That's what I'm doing. Okay, just a 180 degree shift. So that's the angular shift I'm making. When you just look at these two functions, I'm just moving this function to the left by 180. Okay, so that's why when you look at this angular difference, that is what relates to the phase difference. So how are these two functions separated by a given angle? So when you look at this phase difference, then because you're shifting by 180 degrees, the phase difference between them is pi radians, because pi radians is 180 degrees. Okay? So that's the main idea about it. Now, another way of looking at it, which can also be very good conceptually for you, is to just look at this idea of finding the phase difference using the time period. Okay? So in our concept videos, we had learned that when you look at the phase difference, then you can use this formula where the phase angle, the phase difference is just the shift divided by the time period multiplied by 360 degrees. Okay? So what we can see over here is, imagine if this is 0, or imagine if this is the starting point, then, in this case, this entire region over here is going to be one period, because the starting and ending point along this one period, the starting and ending point is the same. So the function repeats itself in after this cycle is over. So this is one cycle, and then the function repeats itself again. Okay? So let's say that if this is the starting point, then this becomes the period t, and then this is t by 2. Okay? And then once you go from t, then over here you just add t plus t by 2, and so this becomes, in this case, this is going to become 3t by 2, and then you add t once again, and then this becomes 2t. Okay? So this is how the time period is changing. Now, once again, if I take this red curve, what you're going to be finding is that I'm going to be shifting this red curve to the left. So once again, look at these blue boxes over here. Okay? Look at how these blue boxes are changing. So as you can see, I am simply moving the function to the left by a time period of t by 2. Okay? So for example, if you look at this leftmost red curve, okay, if you look at this leftmost red curve over here, then what we're doing in this leftmost, if you look at this point, I'm just moving it to the right by t by 2. So if this red line was where the original function was, if I move it to the left by t by 2, I get my sine of t, which is my displacement function. So therefore, in terms of time, the difference between these two functions comes out to a period of t by 2. Okay? So if you look at the phase shift, then the phase angle, phi, is basically going to say that this is shift divided by t times 360. So let's call this 2 pi degrees, 2 pi radians. So we know that the shift is t by 2. You divide it by t multiplied by 2 pi. And so this t will go up. So this is t divided by 2t multiplied by 2 pi. So the t and t cancels out. The 2 and 2 cancel out. And you just get this phi to be pi. Okay? So that's the exact same answer as what we got in the first case. Okay? Now, you can choose whatever option you like best in this case, but it's important for you to know how you get this phase shift. So the reason we use this phase angle or this phase angle formula is that we want to calculate the angular difference, right? We want to calculate the angular difference if we are given two functions with a time difference. Okay? Right? So that's how we look at the phase differences. Okay? So that's for question 16. Now we're going to look at question 17, which is very similar to what we have done before. So in this case, which graph shows the variation with time of kinetic energy of an object undergoing simple harmonic motion with a period of t? Now, what you have to remember is that the kinetic energy is given by 1/2 mv squared. And what you can clearly see over here is that the mass is going to stay positive and v square will also stay positive. Okay? So if you square a number, you'll get a positive number, right? You can't get a negative number if you square it. The only way that would happen is when you use complex numbers, but that we're not looking at those. We're just looking at normal real numbers, not abstract ones. Okay. So anyways, the kinetic energy is going to stay positive when you have 1/2 mv squared. Okay. So therefore, right off the bat, part A and part B is gone because the kinetic energy cannot be negative in this case. So now we are left with two options, which is C and D, right? Now, if you look at C and D over here, then what you would have to see is that you would just have to visualize your simple pendulum. Okay. So in this case, we know that the graph is starting off at 0, and we know that the kinetic energy is 1/2 mv squared. So the kinetic energy is proportional to velocity. So we're just looking at the velocity graph. Okay. So we want to see how the velocity in a simple pendulum changes, because the kinetic energy is 1/2 mv squared, and we can sort of infer how the kinetic energy will change with that. Okay. Now, in this case, we know that the kinetic energy for both of these graphs start at 0. So because the kinetic energy is starting at 0, we know that the pendulum bob will start at one of the amplitude positions. Okay. So in this case, the reason it starts off at the amplitude positions is because at the amplitude positions, the velocity is 0 meter per second at the amplitude. And in this case, the velocity, or the absolute value of the velocity, is maximum at the equilibrium position. Okay, so we have done this in a lot of questions before. If you have any doubts, you can look at the videos where we have done this in depth. Okay. Now, in this case, let's pick a point. Let's say if this is your positive amplitude, and let's say the pendulum bob starts over here. Okay. So what we can see is that the pendulum bob will start over here. It will go to the left, and then it will come back. So this makes one oscillation, or one period, because the starting point and the ending point of the period ends at the same place. Okay. So now, if the kinetic energy is going from the positive amplitude towards the equilibrium position, the kinetic energy is going to rise. Okay, because the velocity is increasing. Then if it goes from the equilibrium position to the negative amplitude position, the kinetic energy will fall because the velocity is falling. And the reason is because that kinetic energy is getting converted into gravitational potential energy. And that's because the maximum amplitude is at a height h over here. Okay. So let's say this red one is part 1, and then this dark blue one is part 2. And then after that, the pendulum bob starts coming back. And in this case, the kinetic energy is rising, because as the pendulum bob goes from negative amplitude to the equilibrium position, the velocity is rising, right? And then once it goes from the equilibrium position back to the amplitude, the kinetic energy will fall. Okay. So if we look at things along one period, what we're seeing is, if this is a period t and this is kinetic energy, then the red curve first shows that the kinetic energy is rising. Then the dark blue curve shows that the kinetic energy is falling. Then in this case, the green curve shows that the kinetic energy is rising again. And then the light blue curve shows that the kinetic energy is falling again. Okay. So that's why in one period, you're going to have two bumps over here. Okay. And that's what we are seeing in one period. Now, if you look at C and D, what you can see is that for C, you have got two bumps, but this is for two periods, so that would be wrong. But for D, for one period t, you end up getting two bumps. And so because of that, D would be correct. Okay. So therefore, for this question, the answer is D, right? And so that's how we looked at question 17 for simple harmonic motion. So once again, you have to understand the simple pendulum, and you should be able to visualize the pendulum when you're doing these questions. Okay, now let's look at question 18. So you have a system that is subject to a restoring force, and it oscillates about an equilibrium position. So for the motion to be simple harmonic, what must the restoring force be proportional to? So in this case, the main thing you need to realize is that the defining condition for simple harmonic motion is that the acceleration is negative omega squared x. So therefore, acceleration is proportional to negative x. Okay? So we know that the net force is mass times acceleration. So in this case, if acceleration is proportional to negative x, then force is also going to be proportional to negative x, because the mass is just a constant, okay? And this actually just relates to the spring constant law, because we know that when force is proportional to negative x, F is equal to negative kx, right? This is spring constant, okay? Or Hooke's law. So force is proportional to the negative x direction. And so in this case, when you have force, then the force is going to be proportional to the displacement from the equilibrium position. So F is proportional to negative x. Okay, that's how the Hooke's law will be working. And if you're wondering how we went from this proportionality sign to the equality sign, the way you think about it is that, let's say if A is proportional to B, then you can remove the proportionality sign and you can say A is K times B if you add a constant over here. Okay? So therefore the answer for this is going to be B. Alright? Okay. So that's good. Now we can move forward and we can look at question 15. This is question 19. That one is just from the past paper. So we can look at question 19. Okay. Now in this case, this is the 19th question for simple harmonic motion. Okay. So now in this case, what is true about the acceleration of a particle that is oscillating with a simple harmonic motion? So first, the oscillation is in opposite direction to the velocity. Second, the acceleration is decreasing when potential energy is increasing. The third is it is proportional to the frequency of the oscillation. Or fourth, that the acceleration is maximum when velocity is a minimum, right? So all of these questions, you can answer them. All of these points, you can see them in your, all of these points, you can simply see it in your simple pendulum, okay? So you need to understand the simple pendulum for doing these simple harmonic motion questions when it comes to MCQs. So we know that at the simple pendulum, you've got your positive amplitude, you've got your negative amplitude, you've got theta, this is negative theta, and then over here, this is your equilibrium position. So we know that at the equilibrium position, the displacement x is 0. The acceleration A is negative g sine of theta. But, in this position, theta is 0. So this is negative g sine of 0. So the acceleration becomes 0. And we know that at the equilibrium position, the velocity is maximum, or the absolute value of the velocity is maximum. So if the absolute value of the velocity is maximum, we know that the kinetic energy is maximum. We also know that at the equilibrium, the height is equal to 0. So because the height is equal to 0 at the equilibrium position, we know that the gravitational potential energy is going to be minimum. That's because mgh, in this case, h is 0 at the equilibrium. Now, if we look at the positive amplitude, then we can see that at the positive amplitude, the displacement x is maximum, and the reason is because this is the frame of reference we are looking at with. And in this case, we know that the acceleration over here is minimum. So the acceleration is going to be negative g sine of theta. We know that the velocity is equal to 0. We know that the kinetic energy therefore is equal to 0. And we also know that at the maximum amplitude, you have maximum height. So because you have a maximum height, you can end up saying that the gravitational potential energy at this point is going to be maximum. Okay. Similarly, you can look at the left amplitude over here. So at the left amplitude, the velocity is 0. Therefore, the kinetic energy is 0. You've got your maximum height. So over here, you have to just see that you're going to get a certain sort of symmetry at this simple pendulum. So these two heights should be the same. Okay. So at the negative amplitude, you're going to have max height. So gravitational potential energy is going to be maximum. You know that in this case, the acceleration over here is also going to be maximum. And the reason is because the acceleration is negative g sine of theta. But over here, because theta is negative, this is negative g sine of negative theta, because you've got a negative theta value over here. And so sine of negative theta is negative sine of theta. So this just becomes g sine of theta, which is why you get maximum acceleration, because it becomes positive. Okay. So you've got maximum acceleration, right? The kinetic energy. Okay. So I think that sort of concludes it, right? And yeah, you just, the main thing is you don't need to memorize all this. If you just do a few questions, then it becomes second nature, right? It's more of just understanding these things, and then they come to you easily. Okay. Now, in this case, what we can see is that, we have seen that once you're at the equilibrium position, the absolute value of the velocity is maximum. Okay. But we have also seen that at the equilibrium position, the acceleration is 0, which is why option D is going to be the answer. Okay. So when you look at the relationship in this case between the acceleration of a particle and the velocity, you will find that the acceleration is a minimum when the velocities are the maximum, so it becomes D. Okay. It's not C, because for C we have found that the time period is 2 pi square root of m by k. This is for a mass spring system. And we know that 1 divided by the time period is the frequency. So therefore, the frequency only depends on the mass and the spring constant for a mass spring system. That's what the time period depends on. So that's why the acceleration is not proportional to frequency. Okay, the frequency does not depend on the acceleration. Right? Now for B, it's saying that the acceleration decreases when potential energy rises, and that's also wrong. The reason is because when you're going in this sector over here, when the pendulum is going to the left, the height of the pendulum is rising, so this means that the gravitational potential energy is rising. But at the same time, as you can see, you're approaching towards your maximum acceleration, so the acceleration is also rising. So that's why B cannot be possible. And for A, they're saying that the acceleration is opposite to the direction of the velocity, then that cannot happen as well. Okay? And the main reason is that, in this case, when the object is going in this direction, right? When the pendulum bob is going from here to here, then the velocity is going to be positive because the pendulum is moving in the positive x direction. But at the same time, we know that the acceleration is also positive in this sector. So that's why A does not work as well. So you're left with this answer of D. Okay? So once again, go through the simple pendulum And I've done all of these questions, and we have done a lot of simple pendulum questions. So if you go through all of them, you won't have any problems with these. Okay? So this is the main idea for it. And